this will be the sixth workshop that we've done, and we'll do a little bit of review on the powertrain from session 5, and then we'll go into a little bit of the analysis done on brakes. I actually did this originally with the team, but the recording in Zoom failed, so it'll just be me in this, which will make this a little bit quicker at least. So the first thing I want to talk about, right, as I said, that I want to talk a little bit about the review of the powertrain. Right, which included the engine and the drivetrain system. So we'll start at the source with the engine. So with the engine, we like to look at pressure versus volume diagrams because those can be related to the work output. And if we drew a little schematic of our engine, right, we might have an intake valve, we'll have a spark plug, we'll have our exhaust valve, right, and then we'll have our piston. Maybe this is our piston at top dead center. We'll say that TDC. And this is the volume at top dead center, right? And then this can travel up and down, right, on the crankshaft, right? And so this is the volume at bottom dead center, right? And so that would include, so the volume at bottom dead center, so let's say volume at bottom dead center, right? And that's going to include all of this, right? It includes, you know, everything in here, right? It's not just the volume between top dead center and bottom dead center. And so in this kind of distance from here to here, call this the stroke of the engine, right? And this is obviously, you know, if this is connected to a crankshaft that rotates from, well, if it's connected there, that's when it's going to be at its very bottom point. See if I can just delete the circle, mess that up, and then draw a bad circle on top of that. Anyways, so the distance from here to here is obviously also the stroke, right? So that's how it's designed. That's how it's designed in, right? And then there's a couple important things about the design. That we care about, and one of those is the compression ratio. So the compression ratio, and that's the volume at bottom dead center over the volume at top dead center. This is, you know, usually, you know, around, you know, maybe let's say on the order of 12 or so for kind of like our formula engines. And so the higher the better usually, until you begin to get limited by breaking things, just because your pressures will get too high, and so you end up having to build things that are stronger and stronger, and then your engine might end up getting heavier and heavier, right? But typically you push to go higher, and that's why you'll see like race engines will have even higher than this, and they'll have to run high octane fuels, right? Because the higher compression ratios, the more likely you are to get knock. Which is basically a flame will start because of the high pressures and temperatures that aren't associated with the spark propagation of the flame from the spark, basically. So it's not always that when the piston travels up that it pre-detonates, but it could even be just after the spark is going that you'll have around the outsides, away from your spark, you'll have little detonations that begin to happen. And usually there's kind of acoustic sensors in your engines these days to help prevent knock, and if they sense it, they'll put in some control from their ECU to help avoid it. probably power your engine down for the most part. Figure out what's actually wrong with it. So you have that, and then you have the, maybe the most common metric about your engine is the displaced volume, which is just the difference, the volume at bottom dead center minus the volume at top dead center, right? So that's the, that's what's listed, when you buy a, 1000cc motor, right? It's the displaced volume that's being listed, or 5 liter, V8 or something. That's the displaced volume when they add it up for all the cylinders, basically. And so if we look at kind of the different processes by which this piston goes inside of here, we talked a little bit about last time. If we mark kind of atmospheric pressure here, so P atmospheric. So we're going to start at top dead center. So this will be the volume at top dead center, and we'll go out to the volume at bottom dead center. Right, so we're going between those two values, right? And we usually will say this is 0 degrees crank angle. So 0 degrees crank angle, and that's when you're at your top dead center. And so you'll typically have sensors in your car these days to sense the crank angle position. But because you actually, remember, you do 2 revolutions for every time you get one of these strokes or one of these phases of your engine. So you actually could use a cam sensor, because your cam will actually spin usually half as fast as your crank. And so that way when you're at 0 degrees, after compression versus, 0 degrees after exhaust, right? Because those are very different parts of the phasing. So if you don't have those, you're actually gonna have to spray twice and spark twice, because you won't know which one of the cycles you're in, basically, which is what we end up doing for our formula engine. So we're going to go, and this is going to be the intake. So we're going to come in, and we're going to come to this point, and so this is the intake portion, right? So the pistons come down, pulling in a fresh charge, right? And that's going to be this is the pressure inside the cylinder, right? And so this must be lower than atmospheric unless it's forced induction, because otherwise, flow goes down pressure gradients, right? So flow is going from high pressure to low pressure. So this better be lower pressure, right? And then we're going to compress, right? So then we hit about 180 degrees, and then we're going to compress this, right? And so this is your compression stroke, right? And then usually a little bit before you're at top dead center, you're going to have your spark basically go. So right here, we'll have our spark. Maybe around 10 degrees. We usually say before top dead center, right? So 10 degrees before top dead center, right? And then what'll basically happen, right, is you're going to get this spike in pressure roughly, right, when you have this, combustion phase that happens very quickly. I mean, it's not infinitely fast because your engine's actually moving pretty fast, but relatively quick, you'll get this kind of little spike in pressure. And so this happens at 360 degrees, right? So you're basically back at top dead center, right? After your compression stroke. Here you're still near 360 degrees. So this is just the spark. So this is just a kind of spark phase, right? And then you're gonna have your, your kind of combustion phase, and then you're gonna have your power stroke. So then you're going to have your power stroke or your expansion stroke. Right, so this is where you're getting all the energy out, or at least most of the energy out at this point. So you have your expansion stroke at this point, and this is going to put you at 540 degrees. So this point here is also too where you inject fuel in manifold. If you have a fuel injector and it's not in the cylinder, typically somewhere around here you inject fuel in the manifold. That way, you about 180 degrees before you need to intake that air in, it's already getting to mix. And then you're going to come down here, right, to 720 degrees, and this is your exhaust stroke. right? And then you have a, I mean, and I'm drawing these as kind of straight lines, but of course they're very rounded if you look at an actual, the actual engine performance. And so, this is going this way, this is going this way, this is going this way, right? And this one's going this way. So these areas depend on the areas, whether they're positive work out, so, or negative depends on whether they're clockwise or counterclockwise. So here you're getting work out, right? Here you're putting work in. So kind of the net work is going to equal your work out minus the work you had to put in, right? And we call these kind of the pumping losses or pumping work, right? Because that's just the work that it takes to, the difference in, you have to push out the exhaust at a little higher pressure than you got to take it in, right? So you can flip this if you have a, some sort of forced induction. So that's one reason to turbo or supercharge your engine. Besides, it'll also just help you get more net work in the network out portion of the PV diagram as well. So what else do I want to say about that? I mean, it's also a reason why you want to make it as easy to get your intake air in and your exhaust air out. Big valves, get the runner lengths right, don't have any restrictions, tight turns, sharp edges and stuff. You want to kind of smooth, make it so it can go in and out of the cylinders as easy as possible. And the other reason to get it in and out is because, actually you can see you don't actually, if you have, let's say red is this unburnt gas in here, there's unburnt gas in here that's going to be left over because you can't completely sweep out the volume of the cylinder. And so, the better you can help get that, pull out that last little bit of spent charge. Otherwise, that's just taking up volume in your cylinder, basically, right? So the better you can kind of exchange the gases, the more you'll get out of this spark portion of the spark portion, right? Because you'll have just more fuel and air to burn. So we also, last time we said this kind of W net is also going to be equal to the volume displaced times, we make this indicated mean effective pressure. And so I is indicated. I think I said that wrong last time. Someone said it was, maybe Rafa said it was internal, but it's indicated, right? And that's to differentiate it from brake. Sometimes you'll see B for brake, and this just means basically at the wheels. So it includes like drivetrain losses. Right, so this is stuff you're putting into the ground. So this includes kind of all the losses of getting power from your engine into the ground. Whereas the indicated is more specifically looking at the output of your engine, right? So if you want to compare whole cars to each other, the brake is probably a good way to do. If you want to compare engines, you should look at indicated. And so in this indicated pressure is basically if you took these two areas, right, and you subtract them from each other, and then you basically would make a plot here to here, right? And you'd say this area here above atmosphere, so this equals omega net, the area does, right? And that will give you P. And so this is a nice metric. It's kind of like, it's kind of how good your engine is, and it's kind of taking out the effect of, of course, a 5-liter engine is going to be producing, or better be producing more power than a 1-liter engine, right? But this kind of normalizes for that fact. One other thing I should just mention is this displaced volume, right? So this is also related to the area of the piston, so it's typically round, times the stroke, right? Which I think I had was green before, right? So you can also, the geometry of that stroke to the area of the piston, right? Because this piston's actually kind of round, right? So if we, it's actually kind of a round piston, right? It's at least typically round. I guess you could try and make something square or something, but right. And then you can even do, and they'll do, of course, different shapes on the top, right? Sometimes there'll be a hemispherical, right? And so you'll, you know, that way you can see, you can decrease your volume at top dead center because it can get more up into that area. And then usually you'll also have little indentations for where your valves will come in, basically, because when it goes to top dead center, sometimes your valves might not always be completely closed, right? So for example, after the exhaust, you know, after the exhaust phase, you might have some valve overlap, and we talked more about that last time. So the other thing I want to talk a little bit about is, all right, so that's kind of what's going on kind of more specifically inside the engine, right? So we talked a little bit about burning octane, which is kind of the example. You know, gasoline's actually made of a lot of different, you know, hydrocarbons, but this is kind of the model one we use, right? And we burn it, right, with 20% oxygen, you know, and almost 80% nitrogen, right? Of course, there's other stuff in here, but, you know, something close to that. And what we basically are going to get out is we're going to get water, CO2, right? So 18 divided by 2 plus 8 CO2 for those, and then you're going to get, you know, 12.5 times 3.76 N2, right? Which just goes along for the ride. I mean, so if you could burn, if you could set, if you could carry enough pure oxygen on board your car, you could actually get a lot more power out, because this nitrogen basically just sits in there as kind of a dead molecule, and you have to heat it up with the flame. So that's actually kind of a waste of energy. And so, but the kind of important part here is you can see with a certain amount of oxygen, you can only burn a certain amount of fuel. You know, so you can't just dump in an infinite amount of fuel into your engine and get more and more power, right? Even if you knew, okay, the energy density of your fuel, right? You have to. There's only a certain amount you can get out. And so, and this is kind of the burning at what's called stoichiometric, which is kind of the perfect mixture. But usually you'll operate a little bit above or below this, just because we'll talk about why. So the air-fuel ratio, right, is the mass of air over the mass of fuel. And we, you know, so if it was by mole, it would just be 12.5 over 1. But we have to convert it with the molecular weights, which I won't bother to go into as much, but it's around 14.7 for gas. It's kind of the classic. So at stoichiometric, so as I drew it above. You can practice with your molecular weights if you want to find that. And so, and we usually look at an air to fuel equivalence ratio, since we don't want to just have to, so equivalence, we don't want to have to remember 14.7. So usually we make this lambda, right? And this is our actual air fuel ratio over the air fuel ratio when it's stoichiometric, which basically means if you're at stoichiometric, you're at a lambda of 1. If you're at a lambda of less than 1, we call that rich. You have more fuel than you need to be stoichiometric, and usually you operate around, you know, maybe 0.9, 0.8 at your highest powers, because that will give you higher power. So that's just basically making sure you're burning all of your air, which is what's really limiting you, you know, in terms of how much fuel you can burn, basically. But then you're kind of wasting fuel typically. You're basically you're kind of really leaning towards getting a high power density, or just high powers out of your engine, at the expense of dumping in extra fuel. So if you care more about fuel efficiency, you might run a little bit lean. So you might run a little bit of excess, and that way you're basically, in that case, you're saying, hey, I care that I burn all of my fuel completely, and you don't necessarily care about the power output. So you run a little bit lean to make sure you have enough oxygen to burn all that fuel. And this will give you higher fuel efficiencies. So I'm going to write A to F. Eta is usually kind of, you know, and so that would be, fuel efficiency would be like, you know, how much work are you getting out of your engine versus how much energy associated with inside the fuel are you putting in, right? And there's going to be some losses. There's also a phi, and this is a kind of a fuel to air equivalence ratio, which just basically means it's 1 over lambda. Basically, you're just inverting kind of the ratio. So keep in mind, sometimes you'll see phi, and of course in that case phi greater than 1 is this fuel to air equivalence ratio. Greater than 1 is rich, and less than 1. But we usually use lambda, and that's just, we talk about that because our AEM engine control unit basically uses these lambdas to calculate how long it should keep the fuel injector open. So then we have, we can say, last time we looked at the power of the engine, and we looked at some of the things that it was related to. So it was related to our fuel efficiency, the volumetric efficiency, which is like how much air can you get in compared to your like displaced volume, right? And so hopefully you're operating pretty high here. This is usually an input in the AEM as well. Then you have your kind of lower heating value of your fuel. This is kind of like the energy inside the, that can be released as heat associated with your fuel. But there's lower and higher heating values, which just have to do with whether the fuel comes in as a gas, which is lower, which you can get less energy out of, versus if it comes in as a liquid. And we usually assume it comes in as a gas and not as a liquid, just because it's usually already evaporated, and so we're not getting the energy out associated with that phase change. We have our displaced volume, right? We have density of the air. This is actually at STP, right? So the volumetric efficiency takes into account any kind of changes associated with the density of the air that's actually in the 2 over your air fuel ratio. And this is all multiplied by your RPM. And this is going to give you weird units, because it's not going to give you horsepower. It's not going to give you kilowatts, right? So it's like you have like a per minute over here on RPM. So keep in mind, if you want some better units, you're going to have to do some conversions from like minutes to seconds, and so in this right here, we also know our power is equal to our torque times omega, like the rate at which it goes, which for, in English units, you usually see torque times RPM over 5252. And this is, if you put this in foot-pounds force, this will give you units of horsepower altogether, right? So that's why you'll typically see this. But, that's kind of a gross unit for engineers, to be honest with you. I mean, I think the logical thing is either to work in, Newton meters and then radians per second, and that'll give you an output of kilowatts just naturally, or you work in foot-pounds and you work in radians per second, and that'll give you foot-pounds force per second. And that's like kind of the common, that'd be kind of, I think, a better power unit to work in English units. Horsepower is just kind of a little bit of a silliness, but it's nice because we kind of know, we have a good intuition about it. So that's the upside about it. So you can see this term, right? This term is going to kind of look like your torque term, right? So this looks like kind of your torque term. So this kind of relates to this stuff can kind of also be related to your torque to some extent. So how do you improve this stuff? Like your fuel efficiency, you want to get your compression ratio up as high as possible. That'll help your fuel efficiency. Those are directly related. Of course, you can get, bigger displaced volumes. That's of course good. You have better intake and exhaust design, as well as, better valving, timing of your valves, right? All that stuff's all that stuff's important. Even the shape of your piston, right? That'll all affect it. And your air fuel ratio, this is a little bit of you can't actually really mess with your air fuel ratio much. Like this basically says, oh, if you want high power, you should make your air fuel ratio basically 0. Just dump in an infinite amount of fuel. But we know we can't burn an infinite amount of fuel. So the air fuel ratio is kind of a little bit of but you can see as it gets a little smaller, it's a little bit better, right? Obviously, if you go above 1, you're hurting your power output, because you're basically just not burning all the fuel you could be burning associated with that air. All right, so those are some of the terms that kind of affect the kind of power coming out of your engine, kind of just at steady state. And so typically what we looked at, so that's, if you're maybe It's just kind of some very basics about engines if you're kind of looking at designing stuff associated with your engine. But usually your drivetrain, you're not maybe getting into as much of that. You're typically maybe looking more at a torque versus RPM curve, right? So you're kind of looking at what's the output of your engine at this point, and you're usually looking at between like an idle RPM and some sort of, you know, I would say maybe we call this like red line, basically, where you don't want your engine to go over anymore. Have some red line RPM, and this will typically come, have some kind of hump, and then kind of start to drop off pretty strongly at these higher RPMs. And then we know that power is torque times the speed. So we know if we just take all of these values and multiply them by their associated RPM on the horizontal scale, we'll get power. So that's going to typically give us, if we kind of draw a power curve, that's going to give us, you know, down here is going to be really low because the RPMs are low, but then that's going to weight these stuff to the right higher. And so what you'll get is you'll see this will kind of come, and then it'll kind of come in. You know, let's go back. So it's going to kind of raise a lot until it gets to the peak, and then it's going to flatten a little bit, and it's going to kind of come down here. So the peak, here's peak power, right? Peak power RPM. So these are all RPMs on the horizontal scale. Right here, we might say is kind of our peak torque RPM. And so the RPMs between these two values, we kind of usually consider this kind of our power band. It's kind of the area where we want to keep our engine. It just usually after the torque kind of flattens out or starts to decrease after it reaches its maximum, that's what you see your kind of power band. Your power will start to be a little bit flatter. So this kind of just between these two areas, and so the wider this is, the better it is for your engine, right? You want a high power, and you want your engine to make that power over kind of a wide range of RPMs, just because it's going to have to operate at a range of RPMs, unless you've got some special CVT system or, you know, some really cool drivetrain, right? So, but pretty much any drivetrain is going to have to operate around its peak. So this is peak power. So right. So this was our peak power. Right. Down here was our peak torque. And don't care. I mean, if these are scaled at different, you know, different ways, these can go up and down relative to each other. I mean, they only cross at 52, if they're plotted on the same scale. So don't get distracted by the fact that they don't cross at certain points or one's above or below the other. I mean, that just totally depends on how you scale the two axes relative to each other. So don't fret about that. And so basically the drivetrain at this point is looking to how can I keep the engine operating near peak power as much as I can. And so if we look kind of at the drivetrain now, moving down. So here we're looking at the drivetrain. Okay, so kind of a simplified model is we'll have some kind of output sprocket or shaft or pulley of some sort, right? And this will give us kind of the rotational rate of the engine times the torque of the engine. And then this will maybe be geared to the wheels, right? And so your wheel will be out here, right? And this will maybe, let's just draw a belt so you kind of, right? And so this is kind of we'll call this R2, and this will be kind of omega 2, and this will be the torque on 2, right? And all this will help us basically generate a force on the tire, and it will cause our tire kind of at the center to travel at some velocity. I mean, it travels like 2 times the velocity at the bottom, so I'm kind of like debating whether I should draw the velocity at the bottom or not. But let's just draw the velocity of the tire. So, or maybe we should call this like, I think how do I want to draw this? We'll just say velocity of the vehicle. We'll just say velocity v. How about that? So we have our velocity v that it's going at. So in this, I'm gonna have some radius 1 in here, right? So it has some radius, and so that the reason I point that out is because we say we define the gear ratio between kind of our tire, basically our output sprocket versus our input is going to be equal to the radius 2 over the radius of 1. So we call that the gear ratio. And of course, typically there's like, could be at least 2, maybe 3 gear ratios. So this could, this is trying to model kind of the gear ratio of your like shifting gears, right? So you have some gears that'll shift. You might have a gear ratio of like your final drive inside your transmission. So like for example, our KTM engine has a final drive, or for Baja, this could be like the gear ratio of the CVT, and then the gear ratio, which is the shifting part, or the gear ratio of our gearbox actually, right? So these all get multiplied together. Gear ratios multiply as they go in series. And then, for example, in formula, we also have our gear ratio of our sprocket, right? So we actually have 3 things that make this up. And you don't need to like, so you can see like what really matters is the product of all these. Not one of these almost means nothing. So like, for example, like I hear all these people talk about like, oh, we're going to use an overdrive gear. It's like the overdrive gear means kind of nothing to us because we can design our sprocket ratio. Or the same thing with the CVT, right? Oh, the CVT goes over 1-to-1. That means absolutely nothing because we design the gearbox ratio. What matters is the product, right? So if this goes to point, unless it matters in terms of the actual system inside the transmission of the CVT, but it doesn't matter in terms of the whole gear ratio, right? Because we design this gearbox value, we design the sprocket ratio, right? So yeah, when this goes to 0.7, but it's multiplied by 10 or 7 something, right? So it's actually the gear ratio is 7. So you're not actually going over 1-to-1, and you never will. I mean, the whole gear ratio is is never going to go that low. Your engine's always going to be kind of spinning faster than your wheels. At least in any of our systems, you'd have to be going crazy fast and have kind of a slow engine to have that reverse that trend. So, but we also know, so the gear ratio, right, in our case, because we're just going to, I just simplified it. I don't want to deal with a bunch of different radii, but the gear ratio in our case is related to how much faster the engine spins over how fast omega 2 spins. It also relates how fast the engine spins to omega of our tire, right? And that's because these things are equal, right? I basically tried to draw them in a case where basically this sprocket here is basically I am envisioning it mechanically linked to our tire, basically, so it rotates at the same rate. And this is also going to be the inverse of the torque on our tire. So the torque on those two are also the same over the torque of our engine, right? So you can see the gear ratio, it decreases the speed, but increases the torque, right? And that's, of course, because power is torque times omega, right? So if this is fixed, right, coming out of the engine, what we're typically doing is we're upping this and decreasing that, right? So you can't get both. So, but we can also relate the velocity, because we know this velocity is going to be equal to the radius of the tire. So the radius of the tire times omega of the tire. So we can also relate this all to the velocity and the force on the ground, which is what we care about in the end. That's what's actually making us go. And so we basically, if we know kind of our velocity is r omega, and we know our omega of our tire is just going to be equal to the omega of our tire is just going to be, we move it all the way over here and divide by the gear ratio, it's just going to be our omega of our engine divided by the gear ratio. So we know our velocity is going to be equal to omega of our engine times the radius of our tire over our gear ratio. And this is that's our total. Keep in mind that's the total gear ratio. And so you can see even the selection of the gear ratio doesn't even matter unless you kind of fixed your tire, right? So it's really the ratio of those two that really matters. And you'll see kind of the force on the tire equals the torque on the tire, right, over the radius of the tire. And I just remember, force times radius is equal to the torque. And you can also just check your units. I always just check, okay, this is a force times length, so I got to divide by a length to get a force. And we know the torque on the tire is equal to the torque on the engine times the gear ratio over the radius of the tire. Which again, we're going to see that the power is torque times omega, which actually, if we plug those two in, the gear ratios and the radius of the tire cancel, and it's just force times velocity as well, right? So you're trading all of these things off, and that's why you can deliver less, you get higher velocities. As these get high, you see the forces will go down. And so at high velocities, you're more likely to be limited by the propulsion of your system and not the attraction of the ground. Right, and so an interesting part, if we look, we can see that the speed of the engine versus the velocity are kind of related in a linear way for a certain gear ratio, right? Let's say you're in one gear. So if we plotted the velocity of our vehicle versus the rate at which our engine spins, right, which could be an RPM. So we'll do like omega of idle, omega peak power. Right, so this is where we want to be. This is where we're starting. So what you'll see is basically the different gearings are different slopes coming out of, we'll draw 3 gears. So this is maybe like first gear, second gear, third gear. And the slope, right, it's going to be omega divided by V. So it's your gear ratio divided by the radius of your tires, that slope. Right, and you can see, of course, the first gear will typically have a higher gear ratio. So that's why it's always kind of confusing when you say you're in high gear or low gear, because if you're in a high gear, like fifth gear, the gear ratio is actually lower. So it's kind of, so just make sure when you're talking to each other that you're not getting confused because someone's saying high gear and low gear. So what you'll basically see, right, so if we're coming in kind of at idle, we actually slip the clutch or the torque converter or the CVT belt, right? And so I'm drawing this for specific gears. And so then it's gonna come up and you're gonna follow first gear, right? And you're gonna have to go way over because you're gonna have to drop all the way down to second gear, right? And so you don't wanna, right when you hit here, you don't wanna drop down here, because then you're operating not around peak power, you're operating way below it. So you come up here, maybe that's a little bit too high. Maybe you'd probably actually drop a little closer to here, right? So you can stay, and you might, typically the power band's flatter below the peak power, right? So you actually typically will stay a little bit on the low end. So let's go backwards a little bit. Come on, go back. There we go. That's right. So typically we'd probably go a little bit over peak power, then we drop down. So we'd probably err on this distance. So this distance 2 being greater than distance 1, basically, right? Just because the power is a little bit lower, but you could run some simulations, right? And we're gonna do the same thing here. We can come here, drop down, and then we're gonna go to here, right? And so this is like FSAE, right? And so you can see you don't get to sit at peak power the whole time. You got to bounce around it the whole time. You basically hardly aren't. Only a couple of, this instance right here, you're operating at it. This instance, you're operating at here. You're dropping straight through it during a gear change, so you're not operating there at all. This is basically an immediate jump. There's no actual time when you're operating there. Baja, on the other hand, so this slip, right, until they get into gear, and then they come up here, and this is where their CVT hopefully is designed to start slipping. I mean, ideally, Baja would engage at, peak torque. I mean, ideally, here you try and want this to be peak. You'd actually want to engage not at idle, but peak torque, right? If you could. And then they're going to come along here until they hit the end of their CVT belt pulling, and then they're going to have to travel along their kind of the high ratio of their CVT. So this is like the low, or this is the high ratio of their CVT. See, I'm already messing up high and low. And this is the low ratio of CVT when they hit their low ratio of their CVT, right? Of course, those are multiplied by their gearbox ratio too. I mean, you see why the CVT is such a beautiful system, but if it deals with belts, right? And so you lose efficiency, a lot of efficiency through the belt, basically. So that's why you probably wouldn't run this system on really a high power system, but it's also light. So that's why Baja likes it. So that's, and so basically, you know, Baja drivetrain and Formula drivetrain should be trying to maximize these values while keeping their system, they should be knowing their torques throughout so they can, have a factor of safety of 3 at least, I think, unless you've done testing. That's the only time you can really drop your factor of safety down, probably to 2 or something. So if you've actually tested it at 3 before and you want to try going 2.5 or something, but don't just design for 2. You should always be designing for 3, maybe 5, depending on if you don't know your loads well. So you're basically trying to, see how this gets you there as fast as possible. So I'm going to stop sharing, and I'm going to and just kind of go over, kind of show you some of the kind of codes that we've written as over time here. So let me see here. I'll just fire them up. So I'm going to stop share. And what we've kind of written are usually some codes so that we can test several different vehicles all at once in the code. Basically, we can look at vehicles either with different sprocket ratios for formula, right? We're going to pick one, around 3, between 3 and 4 maybe, the sprocket ratio, the gear ratio of the sprocket system. Or Baja, we pick the gearbox, right? So what you'll see is there'll be different values associated with the car, right? Like the transmission, gear ratios and stuff, but those are all fixed for each car, and each car is going to go through all of those ratios. But we're also going to have multiple cars with different sprocket ratios and different sprocket ratios or different gearbox ratios, and we're going to be comparing them in those graphs. So that's what we're going to be looking at. So for example, here's our little code for the powertrain of formula. We put in a lot of these units, right? Like gravity, the radius of the tire, drag coefficient, frontal area, density of air, weight of our car, weight distribution, the height of the CG, that affects the weight shift forward and back, wheelbase, coefficient of rolling resistance, traction on the ground. This is like coefficient of friction, or tire people call this the normalized longitudinal forces, going up and down a gradient, the max power. Here's the different gear ratios in our formula gearbox. And then there's also a final drive, right? That's why it's multiplied. So keep in mind, like, these do not matter at all. Like, oh, look, this one goes over 1. That means nothing. It's all multiplied by 2.19, right? What you'll also see is, so then we put in the weight of everything so we can calculate moments of inertia, because keep in mind, for drivetrain stuff, if something rotates, it counts for at least double its own weight, because not only do you have to get it moving linearly, but you have to spin it up rotationally. And that gets worse and worse as it gets closer to the engine, because of that gear ratio. So actually, like, the weight of something on kind of the input shaft of the transmission can be count as a lot of weight on your car. And we put in the drivetrain efficiency, right? So that helps us. We use this kind of as a fudge factor sometimes, just for kind of trying to, so we don't actually know what the drivetrain efficiency is. It'd be nice to know it. The RPM, kind of where we begin to engage, so this is usually, has to be higher than idle, and it's, what's kind of, where are we kind of slipping inside the clutch. Here's our torque curve, basically. So you have to get the torque curve. We've tried to model it, shifting down the peak power by 1,000 RPM and reduced it by 20% based on it being restricted, but we need to measure this, right? You can plot that power curve, basically. We won't do that. Here we just have some functions for calculating the force on the tire, which you can see again, it's just the torque times the whole gear ratio divided by the radius of the tire, the drag force, right? The rolling resistance force, and then we put all those together with the gradient. Here we start to say, oh, we're gonna do a 40-second. We're gonna look at accelerating for 40 seconds. And then here's the different gear ratios of the sprockets that we're gonna try, basically. This just counts these. Here we start to, basically we run through all the different sprocket ratios, right? And then here's where we're actually integrating with time. So we're seeing like, we're basically having to find where we are at the optimal gear ratio. And so we basically see what would be the optimal gear ratio, and we pick the gear that's closest to it, right? So we have to like simulate a driver, and that's how we do it. We don't let the RPM go below the engagement. Find the torque. Here we look at the weight shift and see what's the max traction we have. Here we start calculating some of the drag, rolling resistance. Here you can see we calculate the effective inertia of the vehicle, right? You can even see the percent of that's rotational. We integrate the velocity and distance, and then we just do all this plotting, right? We figure out how long it takes for each different car, the one with different sprocket ratios, to go a certain distance. 246 feet, that's like the acceleration of it, 500 feet, and then we do a bunch of different plots. So that's all it is. So we can take a quick look at what it looks like when this runs. And of course, how long it takes to run is, it's very dependent on how many of these gear ratios you're trying to do, and the time step, and how long you're doing it for. So here we plot the tractive force, right? So these basically, they go until they get into gear, and then they follow the torque curve, basically. These, interestingly enough, you see that you actually shift before you engage. And when you shift, you change the rotational inertia. So you basically, all of a sudden, when you do your first shift here, all of a sudden your car gets a little bit lighter, essentially. And so what that will do when your car gets a little bit lighter, it allows you to accelerate a little bit harder, which puts more force on your downforce on your back wheels, which allows you to get a little bit more traction. So it's actually kind of an interesting, kind of an odd effect, which maybe could be somewhat artificial about which gear ratio you're in while you're kind of sliding. Anyway, so here you can see the shifting. So we look at like purple. So if you have a low or a high sprocket ratio, right, you get to shift a lot earlier, and so you can see you go first gear, shift down to second, to third, to fourth, to fifth, to sixth gear, and then you have to stick in your sixth gear, right? And you might begin to get limited by your RPM and not by the power of your engine, which you don't want. So, and you can see that in some of these cases, right? So the velocity versus time. I don't know why are you going so slow? Oh, these ratios are all too high. None of these are letting you go to peak power, basically. So we can run a couple more, but you can see how basically when you're still sensitive to what gear you're in, your top speed is not limited by your peak power. Your top speed is going to be limited by your top RPM, basically, which we don't probably need to hit our top speed in formula. We're never going to go, if we geared it right, we could probably go 100 miles an hour, right? But we're never going to go that on the track. Your position versus time. So your final velocity. So here you can see that we never went low enough to reach our final one. I'll show you that though. And then here you can also see the time to reach 246 feet. So this is which sprocket car ratio, which car should we pick? Which sprocket should we pick on our car? We haven't gone low enough yet. So let's do a little bit of a range here. So we'll do like 1. No, let's do 2, 3, 4, 5, 6, 7. So we can get rid of these higher ones. So this is running. I can show you. Oh, there it goes. So here you see none of them do that before. They kind of come, and you can actually see this line right here. This is your propulsion limited line. That's what we were calculating before. So you see like they basically come and they try and sit next to being propulsion limited, right? We plotted that line before. See the different shifting. So here we can see like a gear ratio of 2. It looks like you're probably starting to reach. You're starting to be able to reach your top speed where it's power limited. Here you're not, but you see it takes forever for you to get there, so it's probably not going to be that fast. Yeah, you can see this gear ratio. Basically, of 2, it takes a while to catch up to some of the other ones. And so now we can begin to see the time to reach. That's 2, but here you can see kind of 100 times. So you can see around between 4 and 5 somewhere is actually optimal for this set of transmission and this engine. So this is what it's predicting, right? I mean, there's obviously errors in this code and stuff. It's not, I mean, it's not taking into account the time it takes to shift and you know, it's not modeling super precisely the actual kind of engagement of the clutch and stuff like that. So it's not perfect, but this at least kind of gets you in the ballpark. And these times seem to be, as far as I can tell, in the ballpark for what we might be able to do with the kind of our car. So let's also but some people might be like, I get a lot of confusion about about like how the so it's like about the interaction between these gears, right? So we had all these, so you see we had like these really high gears. So like what happens if let's say if I delete these like high gears, basically, right? If we delete these high gears, what you're going to see is, because you don't have these high gears in your transmission, you're going to see it's going to shift the best gear ratio of your sprocket to higher values, basically, because you're going to need those higher values. I'm also going to give you some lower ones here. Hopefully this doesn't break it, to see if we can reach our top speed, basically. I think this 0.5 will probably break it. Let's do like 1.5. Right, and so you see it's really, you can't talk about just the gear ratios inside the transmission without talking about what you pick as your sprocket, because that's really shifting the whole set of those that you pick left or right, basically, for the total gear ratio. So what's actually more important is how many gears you have and the spacing between those gears in terms of their gear ratios. So if you're going to pick like which area, if you're only going to use a certain number, that's what you should be caring about, not the actual absolute values. All right, so you can see, so let's look at, so you can see basically you start to reach your top speed at 2. The only reason this is low, you have to know a little bit about the code, is because it never actually, if you did simulated it longer, a gear ratio of 1 would reach it, but it just basically takes too long to get there. Right, so let's see here. So you can see now it's between 5 and 6 is our top one to go the first 100 feet, right? And that's because I got rid of some of the so it doesn't matter kind of absolute where they are. All it's going to do is shift these times. I mean, I got rid of a lot of your gears, so that's why it made your time go up. But I mean, it doesn't really, and you can also see to go further, to go time to reach 500 feet, will actually catch it. But I'll prove my point here. Yeah, it was 1, 2, 3. Right, so that's the one thing we looked at. We looked at it going 1, 2, 3. So each one of these is a different car, keep in mind, right? So that's what we're looking at. We have basically the different cars. And you can see, we're able to reach kind of our top speed. based on our power limited one. Figure 1. So we see, we're around 4.78 seconds, right? For these ones at a sprocket ratio of 4. So if we basically just double these, so for example 2, 3, 4, what we're basically going to see is we're going to see that we're going to should almost get the same time, but we're just going to make it at a gear ratio of a sprocket ratio of 2, because that's the exact same system. It's the multiplication of these, right? So instead of having those times 4, if you have them times 2, oh, sorry, not 2, 3, 4. I forgot, what was it, Control S or something? Just continue. I forget the command to go to quit. So so it should be 2, 4, 6. Right, so this is basically just, so you can't really say, oh, we need a gearbox with 1, 2 ratios of 1, 2, and 3, which is 2, 4, 6, without talking about the sprocket, right? Because they're because you can basically make those equivalent with different sprockets. So we come down here to this figure 1. So of course we didn't do any ones lower than this, but we got 4.78 again, right? It just happened at 2 instead of 4, right? But it is different to do 2, 3, 4. Right, and that's because the spacing matters about kind of a kind of like a multiplying factor. It doesn't, so 2, 3, 4 are actually closer together than 1, 2, 3, even though they only seem like they're different by 1. It's really about the kind of the ratio of relative to them, right? So for example, we'll see in this case, we still made it down there, but we're a little bit slower in this case, right? So keep that in mind. So talking about, oh, what should these gear ratios be is not specific to that. All right, so we have these. And then, so let's save this. I'm going to close this. We talked a little bit about Baja, which is similar. So the height of the CG, rolling resistance, but instead of having gear ratios, it has kind of the high and low limits of the pulley system of the gearbox. So it has all the moments of inertia, the engines. The other thing that's different, this one actually calculates the bounds, it looks like. The other thing that's different is in the shifting. So the other one, you have to sit in a certain gear. Here, we have different phases where, at first you're kind of slipping, and then you're kind of in the high kind of gear ratio associated with the CVT, then you're shifting, and then you're in the low gear ratio, right? And so we'll see this for different gearboxes. I mean, we also still have this portion right here, which is associated with the weight shift towards the back. So when you go to 4-wheel drive, for example, you can have traction on all 4 wheels. So it's actually, you're going to want a higher RPM, but this is the main thing I think you'd have to change associated with that. So we can hear the CVT ratio, right? So we start off in the high CVT ratio, and then we come down. In this one, we reach the low one. We don't reach it quite in some of the other ones before we hit our top speed. So what's the high one's 11. So the one that's kind of close to good is around this yellow. So actually, we're not even using the full range. Which is a little bit odd, but I think it has to do with the moment of inertia stuff. So the moment of inertia is like very, very significant. And you can see the percent rotational. Where's P? Right, like the rotational inertia could be up to 20 20% basically, right? So it can be a significant weight of the car as the rotational part, right? So you see you get time to reach 100 feet is, good. Seems like best around a ratio of 7, right? But keep in mind this is just a model. It's got plenty of stuff that's wrong. You can reach our top speed. It looks like 27 miles per hour for our car. I think that's because the rolling resistance is quite high. I'm not sure. And so keep in mind that these, if you're putting in these inputs aren't right, then your model's not right. And of course, these are never perfect, but so you want to make sure you get like this, it's very model sensitive to, especially like some of these values, like coefficient of friction between the tires and the ground and these. And so it's also good to test the sensitivity. So, go to try and see which ones is the model sensitive to and not sensitive to, because the ones that it's sensitive to, you need to be more careful about getting those right. Okay, so I think now I'm sharing my screen, which is good. So I got that part. So that's kind of our drivetrain review from last time. It's almost kind of everything, but kind of a review. So at this point, I want to talk a little bit about brakes, which is today's session actually. There's just a lot to review in the powertrain. So the brake section, right? So the most important part about the brake section, both things, they gotta lock up, right? The car's formula, it's gotta lock up and it's gotta keep going straight too. So you need to make sure, your right isn't walking up before your left or something weird, or probably that, your front isn't locking up, way before your rear or vice versa. It might also kind of cause you to skid. So kind of a simplified model of our brake system, right, is you have your pedal, here's your pivot. So here's your pivot of your pedal. This comes down like this, and then you have your driver's foot on the pedal, so right, and so you kind of apply a force of your foot here on the pedal. This is going to go to your master cylinder, and so this has a piston, right, and so this has fluid in it. So you have some piston in it and has some line that comes out of it, right? And that line is basically going to go, so you're going to have a rotor, right, or the disc of your disc brakes, right? And on there, you're going to have you'll have pads on both sides probably, right? And on one or both sides, you're going to have a piston, right, being driven. What's the best way to draw this? Draw this piston. Let's go back. Trade-off between drawing it exactly how it is, and so let's say, so this is your brake pad. So this is your rotor or your disc brake. This is the center line of wheel / rotor, right? I'm just going to set myself up here a little better. So this is going to come in here, right? And this is going to have some fluid inside of here. So your brake fluid, you want this to be pretty incompressible, right? And that's going to press and slow down this caliper. And so a couple things that matter here are, let's say, the radius to the calipers, right, or the radius to the pads. Let's say the radius to the pads. Let's be more specific. Radius to the pads, right? The coefficient of friction between the pads and the rotor is also important, right? The area, on the piston on the calipers, the area of the master cylinder is also important. The length of the pedal to where the driver is pushing is important from the pivot, and then the length to the master cylinder is also important. in this system. Right, and so this is kind of a simplified schematic of kind of pushing this whole thing together, basically. So this is kind of fixed on the other side of the piston. The only reason, you know, putting a piston on the other side just kind of helps make it more symmetric, and also helps bring the bring the pads off of the disc so it's not rubbing at all times. But like, for example, a lot of systems and like bikes and stuff won't actually have both sides move, it'll have one side fixed. So what we care about in all these cases is locking all four wheels. So we'll go back to the physics of that system, but what we really care about is locking all four wheels. That's the requirement, right? Which basically means you have plenty of stopping power. So we need to look at what's the torque needed on the wheel to lock all four wheels, right? And so say we have this tire, the radius of the tire, right? And then we have this kind of force tire, kind of max before sliding, right? And so this is going to be kind of your max coefficient of friction, or more specifically, this normalized longitudinal force, right? Or sometimes this is like n normalized force in the I think it's usually in the x direction. Most higher folks will say is longitudinal. So you have mu max times the normal force. So this kind of mu max, right? And so that's just basically friction, right? So the most force you can take is the max kind of coefficient of friction times the normal force. Mu max for formula, you know, is maybe around 3. For Baja, kind of maybe what designed for is maybe around 1.5 or so, right? And then we see that the torque that we need to get on the tire to do that is nothing more than, you know, F tire max times the radius of the tire, right? So that's the, you know, so that's the kind of torque that we need to be able to get onto this system. So the only thing we don't know really at this point, we know the radius, we know the mu, we don't know the normal force, right? So let's look at kind of a schematic, right? And we did this analysis in the dynamic section, but so here's our CG, right? This is maybe some, we'll call this distance B, some distance C, and this is our wheelbase, of course, right? And so let's look maybe at our front wheels. Those are the worst case, right? We know that the force normal on the front, right? The force normal on the front tire is going to be equal to kind of the static one, the static force, normal force, which is WC over the wheelbase. This is weight, W, weight. And so this just basically says if C is equal to the wheelbase, so if C is equal to the wheelbase, that means the CG is right over the front wheels, right? And so the weight on the front 2 tires, so keep in mind this is for 2 tires, so we should divide this by 2, is going to just be the weight over 2. So this is, keep in mind, so this is per tire now, per tire, so divided by 2, right? But if C is 0, then all the weight's on the rear tires, and this weight will be 0. So this is the static weight distribution portion. And then we need to include the, so this might have some height, kind of the weight shift portion, which is the mass times acceleration. So that's kind of the forces kind of on the CG basically over the wheelbase. Not really forces on the sheet CG, but I don't know. It's one way to kind of think about it, I guess. This is the weight shift. right? And so if we assume that the maximum acceleration is kind of the mu, um, then we can say this F normal of the front is going to be equal to weight, and this will also be divided by 2, weight times c over 2 times the wheelbase, plus, so if kind of the max force you can get is mu times w, so mu times w times the height of the CG over 2 times the wheelbase, and we'll see this F normal on the front is going to be equal to the weight divided by 2 times the wheelbase, right? And put these in parentheses to make that clear. That's not W times B, that's a wheelbase, because it looks kind of like this W, times, we're going to have C plus mu times height of the CG, right? And this is just because this is the max force you can get to help you decelerate is just going to be your coefficient of friction times your weight. I mean, this kind of assumes that there's an average coefficient of friction. Keep in mind this, this is also dependent on this normalized longitudinal force, right? We know that's dependent on the down force, but let's, I think this will typically get you close enough, and you're going to apply a factor of safety anyways. And so if we did the same thing for the force normal on the rear, it would look pretty similar, but of course we'd flip the instead of being the C term, it would be the B term, and it's going to be minus because as you're decelerating, the weight shift goes forward. So this is just going to be this B minus mu height CG, right? All right. So we can multiply those by the radius of the tire, right, to get the torque needed. But so what's the torque of the braking system at this point? So the torque of the braking system. Come on, maybe I should have just done this right after drawing it. So I'm just going to go up and copy and paste this. Copy, let's see, let me paste it in a certain spot. Okay, so we have our system. So the first thing is we know the force of the foot, right? Maybe a person can, we should estimate that. But maybe 150 pounds or something. I don't know. Just put a driver in the car with this, put a scale on the pedal and just push on the scale. So so that means this force of the foot is going to get transferred to the force on the master cylinder. So we have the force on the master cylinder. So MC for master cylinder. And that's just going to be the force of the foot times the length of the pedal over the length of the master cylinder, right? And so that just has to do with the fact that you're pushing at a distance further away. And so this basically just says the moments, right? We did a sum of the moments, assuming it's in equilibrium to get that. Hopefully you're done enough engineering at this point that that's not super shocking. And then if we assume that this is incompressible, right? And that I guess incompressible doesn't matter as much for this, but we assume that this pressure in this hydraulic system is roughly the same throughout, just because it's static. And so we can then say the pressure in the master cylinder, force of the master cylinder over the area of the master cylinder, is going to be equal to the pressure in the system, the hydraulic system, which then is going to be the same as the force on the caliper, the piston in the caliper, I guess. Sometimes you call that a slave cylinder or secondary cylinder, but over the area of the piston on the caliper, basically, right? So that's the force on here. So basically you can see you're amplifying the force on the master cylinder by these lengths, so you can get an amplification there. So you're trying to amplify all these forces onto this rotor. And then you can amplify the force on the caliper by the ratio of areas. So you have area of the caliper over, oops. Right, so the force on the caliper is going to be your force on the master cylinder times the area of the caliper. Yeah, I have that right. Over area master cylinder. So having a larger area on your caliper compared to your master cylinder is going to amplify that force. And then we basically know the force on our rotor is going to be the force on our caliper times the coefficient of friction of our pad, right? So we need that to be high. One thing we should keep in mind too for our tandem systems, because we typically, for Baja and Formula, we'll have kind of these tandem master cylinder circuits. We're going to have to divide this by 2 because typically we're going to have 2 master cylinders. So we should divide these by, divide these by 2 in all these cases. But we will get a multiply by 2 because we're going to have friction on both sides, right? So the torque on the rotor is going to be equal. So this is from tandem systems, tandem. You can even read that. So torque on the rotor is going to be force on the rotor times the radius of the caliper. I think, no, I said radius of the pad, right? That was the distance to the pad, our pad. So the distance to the kind of center of the pad, right? Times 2, because we're doing it on both sides. So if we want to make sure they lock, the torque on our rotor that we're applying better be greater than the torque needed on our tire to lock, right? And we can even divide those and kind of make a factor of safety. So N, it could be the torque on our rotor over the torque on our tire. And we should probably, make this at least 1.5, if not 2, just to make sure we have everything. So the torque that we're getting on our rotor, right, we said basically was, we had the force on the rotor times 2 times our pad, right? So, but this is basically, we're going to plug in the force on our rotor, or maybe like this could be so we have to plug in mu. So we have basically mu pad times force on the master cylinder times area on the caliper divided by 2 times area of the master cylinder times the radius to the pad. And we had 2 2's, so those canceled, right? So that was good. And then we said, but the force on the master cylinder, we said was equal to the force on the foot times the length, the ratio of those 2 lengths, right? Let's try to get my focus right. So we're going to have the force on the foot, right? And then we're going to have length of the pedal over length to the master cylinder, area of the caliper to the area of the master cylinder, and then we'll have R pad, U pad. So that's the top up here, right? If we go back and we get the torque on the tire, right? Let's do this case. So the torque that we need on the tire is going to be equal to force normal on the front, right? Times mu of the tire times the radius of the tire, right? So we'll put this in here. So we have force of the foot, then we have length to the pedal, length to the master cylinder, area of the caliper over area to the master cylinder times the radius of the pad times mu of the pad. And that's all this stuff is going to get multiplied by the radius, divided by the radius of the tire, coefficient of friction on the tire, divided by, in this case, we had weight over 2 times the wheelbase times C plus mu height CG, right? And so this is kind of an interesting formulation at this point. Make sure I didn't see formulation at this point. And that you can see it's basically just a lot of ratios, right? So you have the ratios of the force that you can apply to the normal force, the ratios of the length of the pedal, length of the master cylinder, area of on the slave cylinders to the area of the master cylinder, the radius to the pad to the radius of the tire, coefficient of friction pad, coefficient of the tire. And so you want just generally the stuff on top to be bigger than the stuff on the bottom to help you lock, right? You see how these all make it more likely to lock. All of these things being big make it less likely to lock, right? And so these are kind of, you can see as kind of amplification factors in the middle. These are just kind of ratios. But anyway, so this will all be unitless in the end, right? So you should be unitless. So you got to make sure you put in the right units, right, when you do this little calculation. But first thing is this n, better be greater than 1, and I would probably design it to be between 1.5 and 2, just to make sure I can lock, right? And this is mu max with the ground. That's mu max, right? And this is like mu max with the ground. This mu tire is also like mu max. I'll put in kind of like a worst case scenario. Okay, so let's talk a little bit about designing the brakes. So that's the first thing, right? But you have a lot of, all of these values could really be anything to start. So what I would first start by doing is, one, I'd look at the wheels that we pick. So look at the wheel ID, right? And basically, if you look at the wheel ID, you can basically begin to see, okay, so this is the wheel ID. Wheel ID is how big of a rotor can I start to roughly put in here, right? So I want to get this rotor as big as possible to get the radius out to this pad as big as possible. And I'm going to put a pad kind of on it, maybe right here, but I also need some room for my caliper to get up and around, right? So this is my kind of caliper. Here's my pad on there, right? Right, and so this kind of gives me, and you can look at some other systems to see what this kind of spacing needs to be, but this can give you roughly the radius of the pad, right? So you can kind of off the bat, you can get probably mu pad, mu tire, you can get R pad, R tire, you can get this, and you can get this, and what you're basically designing are these four here. And so what I would basically do at this point is I'd assume kind of your length of the pedal to the length of the master cylinder. So length of the pedal to the length of the master cylinder. Maybe you want to start with something in the 3 range. And with all this information now, you can basically see what is the area of the master cylinder, area of the caliper over the area of the master cylinder. So then I'm going to start to research brake systems where I can get this area right, and that can handle kind of pressures and the forces that you now know about the system, right? So now you start to look at what's the lightest you can basically get this system at this point. And then, so once you kind of find, okay, once you kind of now you find a brake kind of hardware, we use a lot of Willwood stuff, but I've seen other teams even use smaller stuff. What kind of master cylinders am I using? What kind of calipers am I going to have to use? What do the brake pads look like, right? Now you can really hone in and get this radius just right. So your caliper just has, maybe a 1/4 inch of space, between it and the ID of your wheel, right? And then you basically can then get your rotor diameter, right? And so you're going to get your rotor diameter, and you basically do not make this spiky on the outside. That's just dumb. Make it as big as possible, and you want to get your pad basically like right here towards the edge of it, right? And so this part should be kind of the main braking area. That kind of should be your main braking area at this point, right? And then you're going to have a connection to your hub. Typically what you're going to do is you're going to try and angle these as much as you can, right? Right, and the reason for that is that it puts them more in tension and compression than in bending, right? So if you put one like this, when it's holding a torque, you're going to be kind of bending it, where So in this case, when you're, let's say you're kind of applying a torque, it's more likely to put this in tension and compression. So you angle kind of the spokes as much as you can to get them in tension and compression. And so you basically, at this point, you got the outside, you start to look at your rotor connection, you try and get this thing as thin as possible, right? Based on what you can handle in terms of making sure it doesn't overheat so that it's melting, right? And also so that it can handle the stress that it's imposing. You're designing the spokes so that, you're handling the stress. Definitely you're putting like radii in your spokes, right? So this is a solid piece, right? It's got radii here, it's got radii here, right? So this is all solid up in here, right? So you're radii here. You don't want any sharp edges, right? No stress concentrations at this point. And so you're getting pretty close. Next, you're doing some sort of cutouts. I think for the most part, just getting the most part, you're basically, so this is your pen, just to get most of like the brake dust and stuff away. So after it's, the brake pad wears down, basically it has a place to go. I don't think it does much for cooling. Keep in mind that actually your coefficient of friction of your brake pad versus pressure, it's actually going to go down. So if you have too much cutaways or not enough pad, basically, the pressure on your pad is going to go up, because let's say your force is constant divided by your area. So this is kind of you designed for already. And so if this area starts to go down, the pressure on your pad is going to go up. And that's going to cause your coefficient of friction to go down. And that's why if you have too much cutaway or too small of pads, they're going to wear out fast. And two, you're just not going to get the stopping power that you'd expect, right? I was trying to design the thickness, right? Just the thickness and the spokes. And some other things to think about is that the pads, when they come on to your rotor, the only thing that moves them back off typically is the play in the rotor. So there's a lot of friction, can be a lot of friction associated with that. So you might want to, you could design a system where those return basically, or you'll see systems basically that will connect kind of an outer portion of the disc. So here's maybe the outer portion of the disc. Just drawing kind of 4 straight spokes for the sake of clarity. Usually meets it halfway. And what they put is kind of pins. Like, they put like a pin here, pin here, pin here, pin here. This is kind of like this, right? So this is your hub. This is your brake rotor. Or here, maybe this is your like hub connection. So HC, this is the part that connects to your hub. And this has pins that look like this. And then they have kind of, let's see, they look like this. They have kind of spots out here, right? And so what this basically does, so you can see how it traps it so they're all together. It can't come apart, but it gives play to this part, right? And so that allows it to move if you aren't completely aligned. So this is a floating, kind of have a floating rotor system. So you'll see this on motorcycles and stuff, just to reduce friction, reduce wear. You don't need to line things up as well. Some other tricks is to weld if you're going to weld on the tabs for your brake calipers onto your kingpins, is to like weld them while they're grabbing onto your rotors while they're in place, basically to make sure they're lined up real well, or just have them machined to accuracy, right? Some other things I think to think about in your brake system is not letting your brake pedal go over center. So like, for example, so in this case, you apply kind of a force on your brake. Here's the force on your master cylinder, right? This is the pivot, right? And so And so what basically will begin to happen, so here's your, let's say this angle theta, which you want to be less than 90 degrees. So as this gets more closer and closer to 90, actually the component of the force is actually getting the force on your master cylinder is actually getting larger and larger just because of the angle associated with it. But so this is at center, so it's perfectly at 90. But once this begins to go over center, it begins to decrease. So the force on the master cylinder begins to go down. So force on the master cylinder as it goes here is going up. Here it's kind of equal, and then as it goes past, let's say force of the foot is just constant in this case, force of the foot. And this is over center. What basically happens is the force on your master cylinder will start to decrease at this point, and so your driver will push harder and harder on the pedal, and they'll actually get less braking force, which is actually kind of a scary thing. So don't let your kind of pedal go over center. You want to make sure it stays in close to this range, so it stays in this range. And that's why you might have like an over travel switch, which is actually just for your, like, probably more if you lose pressure in your system because you got some leaks. That'll shut down your engine. But also, if you should design it so you aren't going that far over center. I mean, you should also just design it so it's comfortable for your driver's foot and stuff too, right? They probably got like a nice heel rest, and they're driving there for a long time. So I think that's kind of the stuff I kind of get you going on the brake system. I didn't even talk about heat transfer at all. Just like anything else, the more you know, the more you learn you don't know. So, but this should at least get you to the point where you can start to think about locking your brakes, kind of get you in the zone for starting to design it and start to do some, FEA analysis and some heat transfer, and, thinking about kind of the important things that are associated with your brake system.